Hi. Last time we went through the definition of a Turing machine by giving some examples. This time we're going to start by recapping those examples and finish up with the definition of computable functions. Sort of our goal for this very first section is to define what can be done, what's computable. Okay, great. So what we have up here is a copy of something from last time, the computation of the predecessor function. So you see that a Turing machine here. Oops. Keep losing my mouse. There we go. You see that a Turing machine here is a set of four tuples. That approach to defining how computing works makes it seem very much like what a device is actually doing. So this should remind a person, the four tuples here should remind a person of assembly language. Okay, low level and kind of annoying to program in some sense, but nonetheless very, very close to the heart where you have a real sense of doing computation. And we started by putting three strokes on the tape. I mark them as ones in the picture, and putting the machine into state 0. You got to start somewhere, and pressing go. Oh, I'm sorry, I put the machine into state 0 and pointed the head at the very first mark, the leftmost mark, and press go. Okay, everything else on the tape is blank. Right, and of course when we did that, we saw the computation, and the computation was pretty straightforward, that with the three ones on the tape and the machine in state 0 and pointing to a 1, if the machine is in state 0 and pointing to a 1, then you're supposed to go to the right and stay in state 0. So we see the result is that at the end of the first step, we see that the machine head, the read-write head, has moved 1 to the right and is pointing to the 1. Likewise, now we're in state 0 and we're pointing to a 1, so we find ourselves doing the same thing. Move 1 to the right and stay in state 0. Move 1 to the right, stay in state 0. So here we are, 3 steps, all 3 same step. But now something different has happened. Now we're in state 0 and we're pointing to a blank. So a new instruction applies. In state 0, pointing to a blank, move to the left and put yourself in state Q1. So again, it has this very low level, sort of very kind of assembly language feel to it. It feels like you are doing a mechanical computation. And that's the appeal of Turing machines, at least one of the appeals of Turing machines, is that it has a very much a sense of, if you're asking the question, what can be computed, you sure as heck seem like you are actually computing here. Okay, so it seems very close to the metal, as they say. And then at the end, we choose to have the machine halt when no instruction applies. Some authors will have a special state that's designed, Q sub halt or something, and so anytime you want to halt, you go to that state. Okay, so the recap is that it's a very low level, step by step by step. It is a kind of intuitive, kind of discrete a process that seems as though it's what you actually do when you do mechanical computation. You push symbols around. Okay, and of course we think of this machine as computing the predecessor function. If you give it X many ones on the tape, darn mouse here, whoops, there we go. If you give it X many ones on the tape, then if you give it X many ones in the tape, then it will return a tape that contains X minus 1 many ones, although of course if you gave it 0 many ones, then it can't return minus 1 many ones, so it just returns 0. So we think of this machine as computing the predecessor function, so predecessor is one of the things that you can mechanically compute. So there's a certain amount of interpretation here, of course, and we'll talk about that in a few minutes. A certain amount of interpretation of what's happening on the machine. We're not thinking of these as strings, we're thinking of them as numbers. But nonetheless, if we say is the predecessor function something that you could compute, the slightly modified predecessor function, is the predecessor function something you can compute? Yeah, the predecessor function is in the pile of the things that we can actually do on a mechanical device. Okay. 2 more points here before we leave this sort of recap here is that there's 3 ways to think about, to write down what a machine can do. Here's one way, the way that we started out, that a Turing machine is going to be a set of 4 tuples. But this is equivalent, as is this. At the moment, I want to focus on this version right here. So the advantage of this particular table is that it illustrates that the 4 tuples have a Q0 and a B that tells you what's happening now, Q0 and a 1. Q1 and a B, Q1 and a 1, etc. Though the sides of the table, the sort of inputs to the function delta, tell you what's happening now. And then the delta function tells you where you're going. If you're in Q0 and you get a B, you go to the left and you put yourself in state Q1. So delta is a function that takes in the present state and the present character, what the read-write head is looking at, and then delta tells you what to do next. So step by step by step, and delta governs the steps. This is exactly the same thing, only it's written in kind of a graphical notation that sometimes helps when you're working, when you're trying to work with machines. And this here, it's good for the definition, but I gotta tell you, it's sometimes hard to work with. You find yourself looking around, where is Q2B kind of stuff. So this is really very convenient, this delta. Okay, so now we're ready to think about the definition. So I'm going to scoot forward here a little bit. Just the last thing before I go to the definition is that we observe that some Turing machines don't halt. Is that if you have this machine drawn using the little using the little sort of arrow and nodes diagram, or else drawn as a set of four tuples, pictured described as a set of four tuples. If you have this machine, then it doesn't matter what you give it, it will never halt. If you give the machine 5 ones in a row, and then you point the machine to it, well, it's going to start in state Q0, it's got a 1, it writes a 1, which means it doesn't do anything, and it stays in state Q0, so it just keeps looping around and around and around. This machine will never halt. Okay, so that can happen. Okay, so when we go to the definition, we have to take care to have in mind the possibility that the machine doesn't halt. Okay. All right, so here we go. Then the definition of a Turing machine is that it's a finite set of 4 tuples. Each 4 tuple is called an instruction. And we've seen that the present state and the next state and the are elements of the set of states. I always denote them with Q's because you got to do something. I think Q is pretty common. The input symbol or current symbol, TP, that's what you're reading on the tape, is an element of the tape alphabet. Tape alphabet has to have a blank in it because you have to fill out the tape with all the parts of the tape you're not using have to have something, so they're blank. And then the last thing, the action symbol or next symbol, is an element of the action set, which is a tape character or maybe an L or an R. L means move left, R means move right. Okay, so exactly what we've seen in the examples. And then finally here, just to finish, but highlighting the kinds of things that I want to highlight, is that what is most important is that the steps of the machine are determined by a function. If you tell me what is the current state and the current tape character, then the function tells you what to do next. It could be to write a character of the tape, or it could be to move left or right, and then finally what state to find yourself in. So that is the transition function, delta, next state function, that governs what the machine is doing step to step to step to step to step. Okay? Okay, so what we have with the Turing machine then is we have a very kind of close to the metal feel of what you can mechanically compute. And then the rest of this video is going to be just defining the collection of things that are computed by Turing machines. So one thing that arises sometimes when I discuss this material is folks sometimes scratch their heads a little bit, and they have some sense that this isn't like math. That in math it's about like optimizing functions or maybe drawing triangles on the plane. This doesn't seem anything like that. It seems very different. So they sometimes have a sense that this is somehow woolly. This is somehow not really precise. Those folks, I understand where they're coming from. You know, whenever you see something new, there's a tendency to be a little bit like, you know, what's happening here? But I can't emphasize it well enough. What we're doing, the step by step by step, is perfectly precisely defined, and it's defined on this slide here. So a configuration of a Turing machine. A configuration of a Turing machine is a 4-tuple that consists of the present state and the present character on the tape. What's on the tape to the left of the present character and what's on the tape to the right of the present character. So a configuration somehow is a snapshot. It's a picture of exactly what's happening at any moment. And I'm going to skip backwards. I try not to skip around too much. Oops, oops, oops. But these are configurations. This is a graphical picture of a configuration. But just to take an example here, just to pick on some particular one. So right here, after 4 steps, I'm looking at a configuration, capital C, where the present state is 1, because it says Q1. I could write Q1 or I could write 1. It doesn't make a difference. The present character is a 1, because that's what the head is pointing at. Tau to the left is 2 1s, and tau to the right is 3 1s. Did I read that right? 3 1s. So what I had drawn here of the evolving computation is just a list of configurations. Okay, so when it says that the configuration is a 4-tuple, that's this picture only given a slightly different phrasing. Okay, so the configuration of a Turing machine is a 4-tuple. We write C of t for the machine's configuration after the teeth transition. Didn't I just look at C of 4? I think so. And we call that the configuration at step t, step 4. Extend it to step 0, which is what happens before you press the start button. And then how do you go step to step to step? Well, 2 configurations are related. So this is a relationship between 2 configurations. This is the before and this is the after. If you tell me delta, I can tell you how you get from before to after. The transition function tells you how you get from what's on the left of this funny looking symbol to what's on the right. Symbol sometimes called a turnstile, but you should read it out loud as yields. Yields. So configuration at step I, apply the delta, configuration at step I plus 1. And then a computation is just a sequence of from configuration to configuration to configuration. If the computation halts, then the sequence has some final configuration. So we can write that that you start with C0, you end with C of H, and you do a bunch of them in the middle. Star is what we often use to say a bunch. Okay, the rest of the details are details. Exactly how do you apply the delta function? Okay, those details are in the text, but come on. We've done a couple of examples. It's perfectly clear how you apply the delta function. Okay, so that sense that a person may have that calculus is math, but this isn't math. I'm sorry, that's not right. These are all precisely defined. Okay, so having tackled sort of the elephant in the room, here's a very typical example. I have a machine that decides whether the input is an odd number. And just looking at it, what's it got here? 1, 2, 3, 4, 5, 6, many states. And you can trace through the computation 1 step at a time. So I have here a full computation. If you start in state 0 and you're pointing, the head is pointing at a 1, to the left is nothing, epsilon is the empty string, and to the right is 2 1s. Then you trace through what delta takes you to step to step to step to step to step. And you happen to end in Q4, although that doesn't actually matter. And there's a 1 on the tape. That 1 is telling you, yes, what you started with was indeed an odd number, because what we started with was, there we go. What we started with was 3 1s. And I started, of course, in state 0, because you got to start somewhere. Come on, I lost my mouse again. There we go. Okay, so putting a 1 on the tape is my way of saying yes. Yes, it was odd. Okay? Okay, so we are doing computation of what boils down to the Boolean function odd. odd of x, where x is the input number. So this computes the Boolean function odd. You want me to put a question mark after odd? Because it's a Boolean function that answers yes or no about x. Okay? Okay, so we're actually computing the values of functions, and now we want to write down somehow the set of all functions that can be computed. That's our goal for this section. So the definition of an effective function, effective is kind of a bit of an old-fashioned word here. It means a function that you can effect, a function that you can do with a device, intuitively computable. So a function is, of course, is an association of inputs with outputs. That's not about computation. That's just about what a function is. That's just a sort of basic mathematical definition. A function is where you have inputs and outputs and they're associated together. The squaring function associates 2 with 4. The cubing function associates 2 with 8. For Turing machines, a natural computed function is you have a string when you press go, you have a string when the machine eventually stops, if it ever does stop. So the natural association is to associate the input with the output. So here we go. The definition says let P be a Turing machine with tape alphabet sigma. So this is going to be the function computed by T. If you give me a different by P, if you give me a different P, you'll get a different function. The function, you see, that's strings of characters from the tape alphabet, and this is strings of characters from the tape alphabet. Computed by P is you put sigma on the tape, and then the output, phi sub P of sigma, is the string that results from placing sigma on the otherwise blank tape, pointing the read-write head to sigma's leftmost symbol, and running the machine until it halts, if it ever does halt. You might notice that we point to the sigma's leftmost symbol. You need a convention there because it can change what the output is, but where you start the head. So you have to specify that you're starting with the leftmost symbol. I'm in the habit of, I like to end with the head pointing to the leftmost symbol, but that isn't a requirement in the definition. I don't know, just seems neater to me. I just like it that way. Okay, so that's a function that is computed by a machine. We started the chapter off, started the book off, started the course off by asking the question, what can be done? And this is the answer. This is what can be done. Anything that satisfies that definition can be done. If somebody says to you, can you compute the squaring function? Well, you write down a Turing machine that has this behavior, and you say yes, this Turing machine computes the squaring function. Phi sub P squares its input. If for a Turing machine the value of the computation is not defined on some input, then we say that the function computed by the machine diverges. It's sort of an analogy with infinite series. Excuse me. And we write that with an up arrow. Some authors use this symbol that's called bottom, but in this book I'm going to use up arrow. If the function doesn't diverge, we say it converges. If the function converges for each possible input, then we say it's a total function. I'll just remark that sometimes we use the word partial. We might say that a function is partial because the underlying Turing machine doesn't compute the value of some of the inputs, just doesn't halt. And so we might emphasize that by saying that the function is partial, but really every function is partial. The functions that are special are the ones that are total. Every computable function is partial. The functions that are special are the ones that are total, but sometimes we use partial for emphasis. Okay, very important. Not to try to be a nitpicker, but there are some things where you say, well, please pay attention to this item here. There is a big difference between the machine that computes the function and the function itself. Big difference between the machine that computes the function and the function itself. The machine is like the source code. The function is like what you observe just looking at the command line. You type in an input, it computes an output. So if you imagine that you wrote a program to try to square the input, okay, the source code of the program is quite different than the input-output behavior you see when you're typing things on the command line. If you say f of 2 and you get a 4, that's very different. That's an association of 2 with 4. That's a very different than the source code that produces that. Okay, so there's a big difference between the machine and the function that computes them, the function that is computed by the machine. Okay, so again, not trying to make a person crazy about tiny points. This will prove not to be a tiny point. Okay, and another example of the difference is, I know it says it, but another example of the difference is that machines halt or fail to halt, whereas functions converge or diverge. So we'll try to be careful about the terminology in this particular way. Turns out to matter. Okay, one more thing before I get to the functions, before I get to a list of functions: representations. If you want to claim, as we saw earlier, that the Turing machine computes the successor function or the addition of two numbers or the squaring function or whatever function you like. So if you want to say that the Turing machine computes the successor function, what the Turing machine that we produced earlier actually does is the Turing machines that we've shown, they actually start with some bunch of characters on the tape, and they end with some bunch of characters on the tape. That is to say, what we have is that Turing machines go from string to string. The function computed by a Turing machine, input strings and output strings. But we will try not to worry too much, or try not to be too pedantic, too didactic about the fact that 3 marks on the tape represents 3, and we'll be in the habit of saying the function computes the square, so it inputs 3 and outputs 9. We won't be saying that the function takes in 3 strokes and puts out 9 strokes. Every once in a while, in particular in chapter 5, every once in a while we'll have to pay attention to what's happening. But 99 times out of 100, especially in the first 4 chapters, 99 times out of 100, we're just going to say the function that's computed is, and just name whatever it is that we're trying to do. If, for example, let's say we have a graph, this function is going to take a graph and then output, yes, that graph has a subgraph with 4 interconnected nodes, what's called a fork-leak, or no, it doesn't. And we won't say the function inputs a representation of a graph and outputs. We'll try to be as simple as possible. For the same reason that if you take you take something off the shelf, you don't say to somebody, "This is a picture of my mother." You say, "This is my mother." So for the same reason, we won't say this is the representation of a graph, except when we need to. Most of the time, we'll just say it's a graph. But representations are absolutely part of what's happening. Okay, so finally, not finally, but the end of the first section of the first chapter. We started the book by asking what can be done, and the answer is this is what can be done. A mechanism can do all this stuff. A computable function, sometimes called a recursive function, although that's kind of old-fashioned terminology now. A computable function is a function computed by some Turing machine. It may be total function, or it might be partial function, and again using partial to emphasize that there may be some inputs for which the function's output is not defined. A computable set is one whose characteristic function is computable. So we saw, for example, the Turing machine that if the input is odd, output is a 1. If the input is even, the output is a 0. That's the characteristic function of the odd numbers. So a computable set is one whose characteristic function is computable, and a Turing machine decides a set if it computes the characteristic function of the set. A relation is, of course, a set. A relation is computable if it's computable as a set. So less than. Can you compute the less than relation? Takes in 2 inputs, x and y, and outputs 1 if x is less than y, outputs 0 if x, yes, you can compute that. All right, and then the point is that in this brief period of time, we went from sort of 0 to the answer that we wanted, what can be done, and what can be done is what it says in the definition. So what do we end up with? Well, we end up with everything you think of. Everything you think of as intuitively computable is on this list. So all this stuff is intuitively mechanically computable. My handwriting is so bad. Intuitively mechanically computable. So just as an example, you can compute the doublet function. Yeah. You could write a Turing machine that took in a representation of the, yes. Can you compute the squaring function? Yes. You think to yourself, well, sure, I can intuitively, mechanically compute the squaring function. Yes, Turing machine can do that. Can you compute the exponentiation function? I'm not sure I'd care to write the Turing machine for it, but I suppose if somebody said to me, I'll give you $10,000, I suppose I would. You could do it on a Turing machine. Here are some others. Just to pick an example, this is a function that if the input is even, then it divides it by 2. If the input is odd, then multiplies by 3 and adds 1. So you can have cases. This is a function that computes the least prime number greater than x. So you can search for things. Sets, the set of things that are computable is all the things you think should be computable. All the even numbers. These are all the numbers whose prime factorization has 3 distinct primes. So 2 times 5 times 7, whatever that is. 2 times 5 times 7 is in S1, whereas 2 times 3 is not. So all the things you think to yourself, if somebody says to you, can you compute that? And you say, oh yeah, you can compute that. All those things are in this collection. So the collection of computable functions contains, in fact, all of the things that we as people experience with computers or think of as intuitively mechanically computable. And so that's great. That gives a person the sense that that the definition fits. The definition of Turing machine and the definition of computable function fits what in fact can be done. We've captured the notion of effective function. We've captured the notion that answers the question, what is it that can be done? And in the book's next section, the section on Church's thesis, we'll talk about how, the intuition behind that sense that the definition of Turing machine and definition of computable function is the right definition. But just looking at it, it looks like what it seems it should be. It seems to compute all the things you would expect to compute, for example. Okay, very good. See you for the next section. Oops, there we go.